Within this video, I share my perspective and thoughts on how I would recommend preparing for our cumulative final exam, beginning with chapters 1 and 2. How to use this video? I think it's important for a cumulative final exam, or really any exam, to know what to study, to authentically test yourself, and also to transform the instructional material. Knowing what to study can be challenging for a cumulative final exam. So a goal of mine within this video is to identify specific learning objectives that I think are most relevant for your own test. Authentically testing yourself is crucial. You can't just look at a worked example or nod your head and say, yeah, that is how I would have solved it. You need to answer questions and see if you actually know how to do it. In this video, I'm going to suggest relevant questions, but I would not stop there. If you find that it is a question that is not an easy one for you, there's plenty more examples to choose from within the e-text. You need to authentically test yourself and use your best metacognition. Transforming instructional material, you can't passively take an e-text or a video or the most brilliant lecture and think that will be sufficient. That's not what constitutes learning. You need to take that information, transform it in a way that's making sense to you. I think the ideas within this video are things that would be worthwhile to transform and make sense of. I'm placing this within perusal because I think by answering questions for each other, asking good questions, I think together we can help each other learn. So I'd recommend stopping this video along the way. Add annotations that you find important. I'll try to respond to those, but I would not simply watch the video straight through and think that would be sufficient. I don't think that's really supporting your learning. Within chapter 1, here's the learning objectives. To step through these, I think we apply terms like compound, mixture, molecule, phase change, chemical change, homogeneous, inhomogeneous, intensive, extensive properties, and the like, and we connected it to different representations like these particle representations. So we had a lot of vocabulary that we introduced at the start of the chapter. I would look through the e-text. Do you understand the terms in bold in this in every chapter? It's vocabulary, and each of those vocabulary words are representing an important concept. It can be applied with different representations like shown here, but it starts by having an understanding of what the word represents. We introduced the topic of energy, both kinetic energy and potential energy, and as you've seen in the course, we've done a lot involving potential energy. What does the sign of the potential energy tell you? What leads to a decrease in potential energy? When is the potential energy equal to zero? Concepts like these I think we've built on, and they began in chapter 1. We did calculations and attended to significant figures and did unit conversions. Mixed operation significant figure calculations, that was a skill that we worked on in chapter 1 that I think you may need to practice once again. We applied terms accuracy and precision, especially with provided data, and interpreted them to describe which data set might be more accurate or more precise. Here is a representative question. I would expect 1 or 2 dimensional analysis questions, oftentimes including cubic units, so it's relevant for volume. And these are frequently connected to density. Here's a sample exercise problem from the e-text. Like all of the sample exercises within the chapter, you can work on it and check your work. So notice within here we're converting between 60 pounds per cubic foot to kilograms per liter. English conversions like pounds to kilograms would be provided. But I don't think any information would be provided to go from the cubic feet to liters. How do you get from cubic feet to liters? That's the key part of this question. It's something I think you need to be able to practice. Here are representative problems involving density. And here's a cumulative problem at the end of the chapter. I think this is the most difficult within the set. If you're looking for a more advanced problem, I would try to work through this. Within Chapter 2, we had quite a few learning objectives. I list some here, and they go on. So it seems like we have a large number, but let's step through them. An initial one was looking at the key experiments that led to the discovery of electrons in the nuclear model. So we're talking about the works of Thomson, Millikan, and Rutherford. For each one, we want to know the scientist, the experiment, and the significance of their work. I'm highlighting the experiment because I think that is the most challenging part. We had questions where we were looking at general features and then also specific experiments. I know that the figures in the chapter include a lot of information, so I would return to the e-text and try to explore the figures that are shown. I would expect one exam question on this topic. My hunch is you may not remember this information. We haven't been using these ideas throughout the course. So I'd recommend for the exam, same thing I recommended for our first midterm. For each of the experiments, try to summarize and explain each one in a way that makes sense to you. The next skill is something that even though we haven't been using it throughout, I think you'll do quite well on. And those are the symbols that we used to describe for both neutral atoms and ions. We see here Mg2+. Does that communicate the number of protons? How about the number of electrons? How about the number of neutrons? What information is within that symbol? I think you'll do well on a question like that. A skill that we haven't been practicing, but I think that you can get back to it, would be how do we use the atomic weight and make sense of different natural abundance values? Here I give a representative question. Remember, we have two different skills. We want to be able to do a calculation where we, in a sense, calculate what would be on the periodic table, or given the information on the periodic table, how do we calculate the relative abundance of various isotopes? We also connected this to the idea of a mass spectrometer. If you don't remember that section, I'd return either to the class notes, I'd return to the e-text, or ask questions here within perusal. This section right here involving the periodic table, I'm indicating in dashed lines because I think you have that skill now. Being able to look at a formula and determine whether it's a molecular or ionic substance, I think you can probably do that. Similarly, distinguishing between empirical and molecular formulas, understanding how ions are formed, I'm putting that dash because I think you have that skill now. Ionic compounds, I think that's another skill you have. We've been doing a lot with that throughout the semester. So I think you could look at the periodic table to get predict charges. I think you have probably memorized almost all of these common cations, the one in bold. And with a little practice, I think that you've also probably memorized all of the polyatomic anions that you need to know, the ones in bold as well. So this practice exercise, my hunch is that's a pretty easy question for you now. I'm a little less clear about the naming to finish off the chapter for binary inorganic compounds and organic ones. Here's a sample exercise involving binary molecular compounds. If you need more information on this, check out the supplemental information that's shown within the chapter for this sample exercise. The subsequent practice exercises are listed here. I would recommend giving those a try. And that chapter ends with looking at simple organic compounds. Remember, we didn't do a lot with these. We looked at these simple alkanes, these hydrocarbons that were a combination of carbon and hydrogen, where the prefix gave us information about the number of carbons that were present. And we looked at a simple variation on that, which were alcohols.